So in lecture we talked about the hydrostatic pressure distribution being dP dz is equal to minus gamma, and we focused on the case where gamma is equal to a constant. But for the ideal gas law, we have a specific relationship. I should also note that this is equal to minus rho g, and that's actually the form that I'll end up using this in a moment. For the ideal gas law, we know that pressure is equal to rho times r times t. You can see the other technical lecture I posted on the ideal gas law for the connection between this form and PV equals nRT. Or, rearranging in terms of density, we can say density is equal to pressure over RT. And R here is a constant for a particular gas. Temperature, of course, could vary. Let's see what happens if we substitute this expression for density into our hydrostatic pressure distribution. So we have that dP dz would therefore be equal to minus g times the pressure itself divided by RT. Well, we can do separation of variables on this and write this as dP over P is equal to minus g over RT dz. And then just as I did in lecture today, in the case of a constant density fluid, we can integrate this from point 1 to point 2, where the left-hand side is P1 to P2, and the right-hand side is Z1 to Z2. Now the difference in this case is that we have the integrand on the left-hand side, instead of just being dP, is dP over P. So what we're going to get from that is the natural log of P. So let's just consider a particular case where suppose T is equal to a constant. Speck on the screen. So suppose T equals T0 equals a constant. The pressure then integrates to the natural log, so we can write, so we integrate to get natural log of P2 minus the natural log of P1 is equal to, and the right-hand side now, the integrand in this case, with T being a constant, is a constant. The whole integrand is a constant. So we can write this as minus g over r T0 times Z2 minus Z1. Well, the difference between two natural logs can be written as the ratio, the natural log of the ratio. So I can write this as natural log of P2 over P1 is equal to minus g over r T0 times the change in elevation. And then taking the exponential of each side, solving for P2, we can write this as, so the solution becomes that P2 is equal to P1 times the exponential of minus, basically the right-hand side, minus g over r T0 Z2 minus Z1. So it's the exponential of the change in elevation. So you can see this is a little different from the case where density is a constant, in which case the pressure is linearly related to the change in elevation. It's now related exponentially. Now, of course, the key assumption here is that the temperature is constant. If you had some other form, T of Z, you could simply insert that into here, and depending on its form, it may be directly integrable. A common one is that temperature varies linearly, which can then be integrated directly, and it actually gives you another natural log on the right-hand side. With that, you can consider a more general class of solutions rather than limiting ourselves to just constant density. These do rely on the ideal gas law relating pressure and density.